Our team focused on Brownian motion. Brownian motion is the randomly movement of particles when suspended to liquids or gas. Observing Brownian motion requires a microscope, but not everyone can afford a microscope. Our team will give everyone a chance to witness how particles move when suspended to liquid or gas by modeling it using cellular automata. Our cellular automata has following rules. The first one, if a cell contains a particle, then the particle will move out of that cell. The second rule, if a cell doesn't have a particle on it, two possible states might happen. First one, state will not change, and the second one, that cell will contain a particle depending on the motion of nearby particles. Third rule, if a particle moves to a cell that contains a particle, then a collision occurs. In addition, if the supposed to be random location of the particle after collision is not empty, then the particle's location before collision will be its location after collision. We used Euler-Maruyama because we are dealing with stochastic motion. Stochastic means that the increments in location of the particle in the grid is random. Analysis of model. Particles' motion are normalized if diffusion rate is equal to square root of n over t, where n is the number of interval and t is the terminal time. Our code will demonstrate how this normalization of particles looks like. Simulation at the left is running in 25 by 25 grid with a terminal time and number of increments of 100. Number of particles is 100 and the diffusion rate is 1. For the other simulation, same value as the simulation at the left, only time and number of increments are modified with a value of 150. The motion of particles, such as velocity in both simulations, is the same. There is no significant difference between the two simulations in terms of particles' velocity. Diffusion rate equal to sigma affects how fast the particles scatter. If sigma is in the range of 0.5 square root of n over t and with the upper bound of 10 square root of n over t, particles with high sigma move and scatter faster compared with low sigma. To prove that, look at these two simulations. Simulation at the left is running in 100 by 100 grid with a terminal time and number of increments of 50. Number of particles is 100 and the diffusion rate is 0.9. For the other simulation, same values as simulation at the left, but now diffusion rate is 9. Notice that particles simulated at the left with diffusion rate of 0.9 scatter and move slowly, unlike the particles with diffusion rate of 9 where particles scatter and move fast. When sigma is out of range, particles with low sigma move and scatter faster compared with high sigma. Again, let's take a look at the two simulations. Simulation at the left is running in 100 by 100 grid with a terminal time and increments of 50. Number of particles is 100 and the diffusion rate is 10. For the other simulation, same values as simulation at the left, but now the diffusion rate is 100. Notice that particles simulated at the left with diffusion rate of 10 scatter and move fast, unlike the particles with diffusion rate of 100 where particles scatter a bit slow compared with the simulation at the left. The more the number of particles in the grid, the more the particles are compacted inside the grid. Let's see who diffuses faster given that the diffusion rate is 1. Simulation at the left is running in 100 by 100 grid with a terminal time and number of increments of 100. Diffusion rate is 1 and the number of particles is 500. For the other simulation, same values as the simulation at the left, but now the number of particles is 1000. We can see that there are less compacted particles at the left simulation than the right. It indicates that a fewer number of particles inside a container scatters easily than of a container with more particles inside. That's all for our Brownian motion modeling. Thank you.